Welcome back to Beyond the Pattern. So it has been a while since the release of the last video, and we still had a wonderful invited talk that I don't want to keep from you. So we had a guest virtually from South Korea in our lab. That was Jonghyun Choi. He received his bachelor's and master's degrees in electrical engineering and computer science from Seoul National University in Seoul, South Korea in 2003 and 2008. And he received a PhD degree from the University of Maryland, College Park in 2015 under the supervision of Professor Larry S. Davis. He is currently an associate professor of Yonsei University in Seoul, South Korea, and during his PhD has worked as a research intern in US Army Research Labs, Adobe Research Labs, Disney Research Pittsburgh, and Microsoft Research Redmond. He also was a senior researcher at Comcast Applied AI Research, Washington, D.C., and a research scientist at the Allen Institute for Artificial Intelligence, Seattle, Washington. He is currently focusing his research on visual recognition and weakly supervised data for semantic understanding of images and videos and visual understanding for edge devices and household robots. We have had the great pleasure to have had an introduction by him on continual learning, and in particular continual learning in practical scenarios. And I think Jonghyun, he really did a wonderful job in summarizing the state of the art and give directions into the future of research. And I think this talk is definitely a must-see if you're interested in continual learning. So without further ado, Jonghyun, the stage is yours.
Thank you very much for very warm introduction of me, Andreas. And hello, my name is Jonghyun, and I'm studying computer vision and machine learning at Yonsei University, South Korea. Today, I'm going to talk about, as Andreas introduced, continual learning in practical scenarios. Okay, so I'm very glad to see you online, not in person yet, but I'd like to visit you at some point to discuss about the research and something else. Okay. Yeah, so most of AI, you probably know that we need large-scale label data set, and we have some deep neural network architecture to do some task. For example, in this case, we are talking about image classification. But one thing that everyone is missing is that we are only considering that this kind of training is happening once. We call this kind of one batch of training using the notion of data set. But as a human, we are learning something continuously from the environment and some information that we are facing every day, right? So as a human, that we get to know something new, and also we forget something that we have learned in the old days, and we are just continuously updating our knowledge base throughout the time, right? As in the course of time. But in the machine learning, we're not having that kind of notion that we can continuously update the model. We're not continuously updating knowledge that we have once learned in the past. So I think it is more futuristic notion of learning for the machines and also for the humans. So we are probably have this, we may have this kind of loop in the future that human can provide more data, and this data can be taken by the machine, and machine generates some knowledge by its superior characteristic or superior functionality to memorize something or have some reasoning on the provided data. Then on the knowledge that machine can provide, human can also get some other insights so that they can generate other kind of data, so that machine and human can evolve in a proper cycle or beneficial cycle in some future. That is maybe some futuristic scenario of learning between human and human and machine. But learning this kinds of new knowledge in a continuous stream of data is not a new problem, because some relevant topic or some relevant technology has been studied for a long time in machine learning literature and computer vision literature. For example, to name a few, we can think of this transfer learning as one of the study subject that we can think of, we can use for the continual learning. Also, the domain adaptation, that some of the data that looks very different from the existing data distribution, but they are actually in the same semantic meaning. So they have actually same semantic meaning, so that we can add on or we can generalize to the new images in the different domain that in the different distribution, but in the same semantic, but maintain the same semantic meaning. So that is a domain adaptation. And the multitask learning, if you span up this multitask learning into the time axis, you can think of pretty much the multitask learning is a snapshot or compressed version at a one-time time snapshot for the continual learning. So that is the other relevant topic in machine learning literature. Also, method learning or prompt engineering that is recently emerged in the NLP literature, also gradually adopted in the vision literature as well, is also very closely related to the continual learning literature. And if people say the continual learning in machine learning literature or computer vision literature, they usually refer to this notion of class incremental learning. So the class incremental learning is an instance of continual learning, so that you can think of different type of continual learning is also another type of continual learning. But if people say continual learning in the paper, that they usually refer to this class incremental learning. So I will just introduce, and I will stick with the concept of class incremental learning for today's talk. Right. So this class incremental learning is a scenario that class is added incrementally as time goes by, and we are training our model in a batch-wise manner. The batch manner of class set. So here you can see, instead of having all data given to train a model, we are having some small subset of the data as a batch. And then we have another subset of the data as another batch to update the model that is already trained. And also we are getting another subset of the data to update the model further, and goes and goes and goes. So that is the scenario of the class incremental learning. And this class incremental learning will suffer from the catastrophic forgetting. So the catastrophic forgetting is a phenomenon that every neural network is suffering from. But not even just in the continual learning context, but also just learning in the batch-wise manner. So it's learning with every data that is available. In that situation, you're also experiencing this catastrophic forgetting, which is the phenomena that the knowledge that is learned in the early stage of the epoch will be forgotten in the later stage of the epoch. So you all know about this catastrophic forgetting, right? And this catastrophic forgetting is going to be much more serious in the class incremental learning, because once you see this data in the first batch, and the second batch of when second batch of the data is coming, your first batch of data is not available to reuse for the training. So this catastrophic forgetting for these batch of data will be pretty much forgotten forever. So that's why this catastrophic forgetting will be much more serious problem in continual learning. And also it is suffering from the resistance of learning a new knowledge. So I will give you a question. So what is the best way to prevent this catastrophic forgetting if you are in the situation to learn this model in continuous manner? What is the best way? The best way?
Probably to have all the data.
And probably you have all the data. That's one best way, but it's not, we don't have that luxury yet. So given the situation that you're having, the data is coming in the stream, then what is going to be the best way to not forget everything? Then
Then
Uh,
probably to preserve the original weight and just add on top.
That's right. So we're not learning anything new and just having more capacity or something like that. That is one strategy, right? So one best way to not forget anything is that we are not learning anything. So that is the best way. So, but still, we have to learn these new knowledge, right? So here we have a trade-off between learning a new thing and not forgetting the previous one. So that is a two different trade-off, the two different factors that we have to balance in the situation that they're in the trade-off relationship. So this kinds of phenomena is called plasticity and stability dilemma in literature. So this plasticity is referring to the power of learning a new knowledge, and stability is a power of not forgetting the previous knowledge. So these two things are in dilemma, so that we have to get the sweet spot between these two trade-off relationship. So to tackle this problem, people usually adopt this idea of or notion of episodic memory. And this episodic memory is a small subset of training samples vault of previous data, and it is used in the rehearsal-based continual learning method. So I'm going to talk about the nomenclature or the taxonomy of continual learning methods in the literature that is categorized by the European researcher Tin Tutula. You probably know her, right? So a rehearsal-based method needs to address the few-shot learning on the subset of the previous data's sample, and imbalanced learning with the we have to address the imbalanced learning with the previous small subset of the sample and the new task sample that is usually given in abundant manner. So here is the taxonomy of the continual learning methods. So first one is the replay-based method using the episodic memory. So if you have this episodic memory, so that you can store some of the previous data and then replay when you learn a new thing, so that you can maintain some of the knowledge or some of the information from the previous data, previous task. So that is called rehearsal-based method. And the pseudo-rehearsal-based method is referring to the situation that you may not have this episodic memory to store the actual sample, but you may have some generative model, for example, to reproduce the previous data's sample. So that is a pseudo-rehearsal-based method, so that you can remember by using external memory that may be a model to generate a previous data sample, so that you can replay that when you're learning a new knowledge. And the constraint-based method is using the small subset of the sample to constrain the learning the current model with the new data. So that is the replay-based method. So that is the three things. And the regularization-based method is not using the episodic memory, so it's not using the previous data explicitly, but they're using the previously learned model to train the new model as a regularization factor. So it can be decomposed, it can be further categorized by the prior focus method and the data focus method. The prior focus method is using the previously learned model as a prior, so that your newly trained model is not going to be super far from the currently trained model. So that's why, by using the L2 norm of the parameter values of the previously trained the model and the newly trained model. So it's not, it's enforcing the newly trained model that is not super different from the previously learned model. So that is a prior focused. The data focused is slightly related to the replay-based method. So they are looking at some of the previously available data, so the prior data, to be used as a regularization method. So it's similar to the constraint-based method in the regularization-based method category in the data-focused manner. And the parameter isolation method is what Professor Andreas Meyer was discussing. So if you have fixed size network, then you're having the previously learned model, and then you're having another model that is learned on the new data. And somehow you merge these two two network into one fixed size network. So that is the parameter isolation method. So the idea here is to learn a new thing in a separate network and then merge them later. So that is the idea, while you're not hurting anything that is learned in the previous data. So that is a fixed size network. And the dynamic architecture is exactly what Professor Andres Maya was talking about. So you have like gradually increasing capacity of the neural network, and then you're using the new network for learning the new knowledge as the task goes by. So in that case, if you're getting some sample for inference, you have to determine which model you're going to use for inference. So you have to get to know what task that this sample is going to belong to. So you have to have another model to determine which task this sample for inference is going to be belonging to. Then we are getting the model for that task and then inference on on the model for that sample in the inference phase. Does it make sense? So that is a dynamic architecture, and it requires heavy capacity increases as the number of tasks increases. Okay, so here people focus on usually the rehearsal-based method more because it is very simple and it does not require big memory overhead, because usually this episodic memory is very small. And then the practical data is giving us very good accuracy because we are having the previous task sample explicitly. So we are preserving the information without any damages compared to the pseudo rehearsal based method. Does it make sense? Any questions here?
Absolutely.
Okay, cool. All right, so I have mentioned about this catastrophe forgetting, and this catastrophe forgetting in a formal version is the tendency for knowledge of previously learned tasks to be abruptly lost as information relevant to the current task is incorporated. So that is the definition of the catastrophe forgetting that is defined in 1989. And in the continual learning context, the incremental learning model or continually learning model, especially from this phenomena, is it learn a sequence of tasks. So you're not accessing the previously learned the data anymore if the new task is given. So that's why catastrophe forgetting is the center of a problem or the center of the issue on the continual learning study. And there are many setups in continual learning study, but this is one of the most trendy or popular setups in continual learning. So the samples are given in this manner as time goes by. So here the color is denoting for the class, okay? And even though the samples are supposed to be given in this manner, they are rearrange these sample into the disjoint subsets by the classes, and then define each of the tasks by the set of classes. So here, each of the tasks are not sharing any class information. And at the same time, we are not having these samples in this kinds of unordered manner, but rather it's ordered manner nicely to be provided to the model to train the model. Does it make sense? And this kind of setup is called disjoint subset or disjoint setup. So we have a clean partitioning to the clusters of class called task, and typically of the equal size. So here, if you see, each of the tasks has composed of 10 classes. So the first task is composed of the class 1 to 10, and the second task is composed of the class 11 to 20, and the third is 21 to 30, and things like that. All right? So this kind of trendy setup is pretty unrealistic if you think of, right? And also people train the model on this task, which is a set of classes using multiple epochs. Okay, so when they see this task in a batch and they're training their model multiple epochs so that they are learning it pretty well. But if you're thinking about real practical scenario of continual learning deployments, you're having some model and as data is coming in this unordered manner, you have to train your model at instance. And then you don't have a luxury to train this kinds of thing by storing them in a nice batch of data, which is a task in a multiple epoch, but rather you're just learning this thing in a one shot and then just go and then get another data and just train one shot and then just go forever. So in that manner, we don't have much of time to learning this kinds of data in a multiple epoch. So learning this model in multiple epoch is called offline training. But as people realize that this is not really realistic, then they're more shifting to the online manner of training that only allows one epoch of training of the data. So that is a trendy setup that is evolved from the offline setup. So conventionally, people try to get this disjoint task setup with the offline training to train the continual learning method, which is pretty not realistic to the practical scenarios, right? And sometimes people also assume that when the sample is given in inference time, they know which task ID that this sample is belong to. So the task ID, if you have this nicely disjoint task definition, then once you get this class ID in inference time, then, I mean, if you know the class ID, then you don't need to have to actually predict it, right? But at least they are asking that what kind of task that this sample is belong to. So for example, if you're having this sample for inference that is known the task number, then we are pretty much confining the candidate classes by the set of classes in that task, right? So, which makes the problem much easier. So that is also pretty unrealistic and easy setup for continual learning. So people think that this is not really practical or realistic, and people try to come up with different type of continual learning setup that can make this unrealistic setup much more realistic. So the first one is the blurry continual learning setup. And so when you see this continual learning task definition, each of the tasks doesn't share any classes. So each of the tasks has disjoint group of classes, but this is really unrealistic. Some of the classes may be overlapping over the task, right? And some of the samples are appearing over the course of different task boundaries. So people come up with this new notion of continual learning setup called blurry, and each task has a major class and the minor class in the setup. So the major class is the classes that is appearing most, and the minor classes are the classes that is appearing the least. So if you think that, so for example, if you have this blurry 10 setup on CFAR, 10 data set with 5 task configuration, meaning that one task has 2 classes, okay? So each of the tasks has 2 classes. If you're having this joint setup, then you only have these 2 classes in the first task, and the second task, you only have different 2 tasks, 2 classes and so on. But here, the blurry task, you have 90% of the sample is coming from the class 1 and 2, and the 10% of the sample is coming from all different classes. So that you're basically implementing this idea by the notion of the major class and the minor class. Does it make sense? So that is a blurry setup. So here we are relaxing the constraint that each of the tasks is not disjoint anymore. So that is a blurry task, okay? So in the illustration, we can compare the disjoint setup and blurry setup in more visually pleasing manner. In the disjoint setup, if you're having these 2 classes in the first task, you're having only these 2 classes and no samples from these classes. But in the blurry setup, you're having 90% of the sample from these 2 classes, and the 10% of the sample can be coming from these different 4 classes, okay? And as the task goes by, we are changing the distribution of the major and minor in this manner and blah, blah, okay? So here, in this method called GDOM, that is proposed by the Oxford group, and they propose a simple unifying approach for either disjoint setup and the blurry setup. So first thing is to get the greedy balancing sampler for the episodic memory. So they greedily store samples in the memory by maintaining the balance between the number of samples across the classes. So they just randomly sample in a greedy manner, and then just store that in a balanced manner. And they learn the classifier from this episodic memory only, from the samples of the episodic memory only, from the scratch. So they call it as dumb learner. So when asked when the new inference was requested, they train a model from scratch only using the current memory samples and combine prediction with the oracle task information via binary mask and inference. They can get the outputs with the dumb learner. So they require the oracle task information also, which is kind of easy setup. But in this GDOM paper, they empirically show that this greedy balancing sampler plus the dumb learner actually outperform all of the previously proposed method in many different setups like disjoints and blurry and many more. So here they have like some striking, they have discovered this kind of striking fact that the previously proposed sophisticated method is not necessary, but just using this kind of simple method, you're dealing with much more realistic setup of blurry as well as the disjoint setup by the simple method. So that is the idea of the GDOM. And by looking at this GDOM, and this paper is accepted and presented in ECCB 2020 as an oral presentation. And when we are looking at that paper, we are thinking that, yeah, we maybe do better than this greedy sampler, right? And this episodic memory, we can manage this episodic memory much better than just having this greedy random sampling. I mean, even though they're just making the balance between the classes, but still their sampling method is greedy random sampling. So we are thinking about this core set problem. The core set, the notion of a core set of an input set is a small summation such that solving a problem on the core set as input probably yields the same result as solving the same problem on the original, the full set for a given family of problems. So that is a core set idea. So we are looking at this core set idea, and there are many heuristic ideas on how to find the core set from the full set. And one of the idea could be similar to my 10-year-old idea for finding the core sets. Here, I was working on this a few shot semi-supervised learning problem. So given a small initial training set, how can we extend the training set by using non-labeled data, by pseudo-labeling of these unlabeled data from this given training samples? Here, I was learning, so I learned the lesson that when you enforce the diversity in the unsupervised learning, the unlabeled data pseudo-labeling, when you enforce the diversity in the pseudo-labeling, then the improvements on the initial training sets, the augmented initial training sets is maximized. So I was learning that the important lesson that the diversity in the pseudo-labeling or diversity in the core set for the notion of this class label, which is the Dalmatian dog in this class, in this case, is very important for improving the classification accuracy. So here, I use the same idea to manage the episodic memory by diversifying the visual information of the data. So we call it rainbow memory because when you have this diverse set of samples in the memory, then we think that this is kind of similar to the LGBT or rainbow kind of connotation here. So we just name it as rainbow memory for making your episodic memory visually diverse. So the idea is very simple, and this is not the only way to implement the diversity, but this is one of the ways. So we select the representative sample by transforming the original sample as a transformation by the transformation that is used in the data augmentation. So by rotating it or half corrupting it or color shifting or color jittering and things like that. So we just transform many different ways of a sample and pass through the neural network that is currently trained and getting the confidence measure and see the variance of this confidence measure of these transformation of a sample. So when the variance of the transformation, variance of the confidence varies a lot, like when the variance is large, that we think that this sample is not that much confidence in terms of the knowledge that is learned in this current neural network. So if the variance is small, then we believe that this neural network has learned this sample pretty well. That is kind of robust to the many different types of the transformation. So we are defining this variance of the confidence of transformed input as an uncertainty. So if the uncertainty is high, then we think that the sample is not much learned by this neural network. And if the uncertainty is low, then we are thinking that we're considering this sample is well learned by this neural network. And we are getting from very well learned samples to the pretty poorly learned samples by the number of, by the equal distance in this scoring function to fit the budget of the episodic memory. So for example, if we can sample like 100 samples in the episodic memory, then we are sorting all the samples by the score of this uncertainty, and then sample them the 100 things by the equal distance. Does it make sense? So if you have like 10 samples, then your stride is going to be 100. Sorry, the 10, if you sample 100 samples. But if your budget of the episodic memory is 10, then you're having the 100 stride in this scoring function by the sorting all the sample on the uncertainty measure. Yeah. Okay. So using this greedy sampler. Okay, by the way, when you abbreviate this name of rainbow memory to RM, then this is the leader of the BTS. So we just make this name much more memorable to people, right? And also to amplify the diversity of sample in the episodic memory, we are using data augmentation on the episodic memory when you're training the neural network for the new samples. So previously, no continual learning method is proposed to use this data augmentation on the episodic memory sample, but we are just proposing here, and also study many different types of the data augmentation technique of when you're using the samples in the episodic memory. Okay, so here we are doing various experiments using the blurry setup and also the disjoint setup, and using CFAR10, MNIST, CFAR100, and ImageNet datasets. And we are comparing with some state-of-the-art methods on continual learning, like EWC and artwork, the random work, and ICAR, and GDOM, and BIC, and on the 3 different data sets, on blurry 10 setup, on online, and online here, we are only looking at the sample once when you're updating the model. And comparing to the previous state-of-the-art, our simple rainbow memory achieved superior performance even without the data augmentation. And if you're using data augmentation, usually the performance boosted a lot. And on different blurry portion, say different blurry 0, which is disjoint, the equivalent to disjoint, right? And blurry 10 and blurry 30. So here 30 is the portion of the minor classes, right? And our rainbow memory improved the accuracy a lot on online setup. And offline setup, some of the previous state-of-the-art achieve better performance than ours, but the gap is not that big. Like here, the gap is really minor, the gap is small, and here the gap is pretty big, but in the disjoint setup, we're not having anything special for disjoint setup also. So we don't know why, but here this is the some of the phenomena that the ICAR superiorly performed, but in the other blurry setup, this rainbow memory overall performs much better than other state-of-the-arts. And also we tested different augmentation methods on the episodic memory. We used cut mix or random aug or auto aug or cut mix plus the auto aug. At the end of the day, we are using the auto aug because it's just empirically giving the best performance. And comparing to the other methods, our rainbow memory react augmentation methods the best by giving the best performance improvements. And also we compare with different sampling methods as opposed to our uncertainty-based sampling methods. The first one is the random unbalanced sampling method, and the reservoir sampling method, and the prototype sampling method. The prototype sampling method is similar to uncertainty, but they are computing the uncertainty, but it's not uncertainty. So the prototype method is computing the prototype, which is a mean of a sample for the class. And they're getting the sample from the center to the edges, which is close to the classification boundaries, by the equal distance. So here, their scoring function is the distance from the core of the classes, which is a prototype. So that's why they name it as a prototype sampling. And compared to these different sampling methods, our uncertainty-based method is having pretty good accuracy improvements. And later, we found that this random sampling is not balanced, as I said. And when we are comparing with the random sampling with the class balanced maintained, as the GDOM does, we found that the random with the balanced sampling is pretty similar to the uncertainty-based method's performance. So, which was pretty surprising, but we found it later after we submit this paper. To summarize, we tackled disjoint setup on continual learning and analyzed various setup, and we proposed this memory management scheme using data uncertainty, and also show the data augmentation significantly improves the performance in online blurry continual learning setup. And we released the code public in this GitHub repo, and you can download it to reproduce all of the results of the previous method and our methods. So here we study the blurry continual learning setup by using this rainbow memory scheme, but one thing we have just found that, yeah, this blurry setup is actually a little bit realistic, but not super realistic, because when you're thinking of this minor and major class, from the beginning, as a name of the minor class, you're observing all of this, the sample from all of the class from the beginning, from the task one. So it's not actually the class incremental, right? So here, the disjoint setup is actually having the class incremental setup, because you're getting a sample from a unseen class in a new task, right? But in the blurry setup, you're allowing all of the sample coming from all the classes. So you basically have no class is unseen at the second task. So from the task one, you're looking at the sample from the old classes, even though they're in the very low portion. So it's kind of very big imbalance learning problem, but it's not actually the continual learning problem. And one more thing is that this disjoint setup may be unrealistic, but in the catastrophic forgetting perspective, it is the most difficult setup, because you're looking at new task that is having the unseen classes. So in the sample in the previous classes will be forgotten in the next task. Does it make sense? So in terms of catastrophic forgetting, the disjoint setup is much more difficult and challenging compared to the blurry setup. But the blurry setup is more realistic and practical setup, right? So in the actual continual learning deployment scenario, you may be seeing the blurry setup much more than the class incremental learning. So we try to get the best of both worlds. So we propose this blurry setup that has blurry setup based, but has some portion of the classes will be added incrementally. Okay, so we first split all the classes by n% that is going to be used for the disjoint setup, and the other portion will be used as a blurry M setup. So here, if you have this 50% disjoint and 50% blurry M, then the blurry M here is going to be 10%, let's say. Then you're using the 50% of the classes as a blurry setup, and the other 50% of the classes will be added incrementally as task goes by. So then we are name it as iBlurry, the incremental blurry setup. So this much more realistic that we believe setup that we can also start from some baseline methods that we can come up with in this manner. So it's the baseline method is nothing very surprising and interesting, but it's just basically very similar to the rainbow memory, but rainbow memory requires a lot of computation to compute the uncertainty by transforming the inputs and getting the confidence and see the variance. So here we are just looking at the loss value of this currently trained model for each of the sample and see how much the loss is how much the loss is affected by the new sample in the online stream by the currently trained model, and see and getting some of the sample that is not changing the loss much, then we are believing that, yeah, this sample is pretty well learned by the current model. So we are not anymore necessary to maintain in the memory. So we just, pull it out and just discard it to the trash can. And then when the new sample is coming in the online stream manner, then we are just testing these samples in the model and just putting in the memory and just testing whether this is affecting much in the model and whether we are discarding it or keeping in the memory. And so we are having much more simpler method of managing the episodic memory, and using this very simple baseline method, we are achieving pretty well, pretty good performance in the I-blurry setup and also the blurry setup and the disjoint setup. So here, the sample memory management add all new samples and remove minimum loss decreasing samples because they are the least useful for training. And also we are doing the memory only training that we have done in the rainbow memory and GDOM. And we also have this little small trick that the adjusting the learning rates adaptively as the epoch goes by. So it's not very important. So you can just take a look at it in the paper if you're curious about it. And the other thing that we are proposing is that this continual learning methods should be evaluated, and each of the training sample is coming in when you update the model. So each of the data is coming in the stream, then maybe at any time you can be requested for the inference, right? But previously, we have a notion of task, right? So we have a notion of a set of classes to be trained in the continual learning method updates, and each of the task boundaries we are evaluating the model, right? But actually, when samples are coming in, we may be updating the model, and when each of the sample is coming in, the model is going to be incrementally updated in the middle, but we are making this model update gradually using all of the data in that task and evaluate our model at the boundaries of the task, right? But maybe at any time, your model is going to be asked to inference. At that moment, your model's accuracy may be very, very low because you're not using all the samples of your task, of your currently given task for updating the model, but it's just looking at the currently entered model in the stream. So your model is not sufficiently updated. So we think that this kinds of evaluation metric is a little bit artificial. So rather we have to evaluate model at all instances of the data incoming. Okay, so when each of the data is injected to the model update, we have to evaluate the model. So that is our new proposal. So we propose a new metric of computing the accuracy over time and get the integration of it. So the integration requires a lot of continuous function evaluation. So we just having some quantized version of it, which is called average under the curve. So we define a new metric called accuracy area under the curve, as opposed to just getting the average accuracy of the task boundaries. So in the case of the rainbow memory, if you're computing the average accuracy that is computed on the accuracy at the task boundaries and average them, then we get the 61% accuracy. But actually, when each of the samples are coming in, the model is not actually updated, but we are just updating the episodic memory. So if you update the model with the episodic memory that is coming in, currently updated, then your accuracy is going to be very small because you're not using all the samples of that task yet to update the model gradually. So the AAUC is going to be very small. And when you unfortunately ask this model to inference something in this time moment, then your accuracy is going to be like 20%, as opposed to that the average accuracy reported is going to be 60%. So which is kind of a big gap. So that's why we are proposing to use this kind of new metric. And our new baseline is achieving pretty similar value of the A average and AUC, because our model is updating the episodic memory when every data is coming in. So it's having much more frequent model updates and also maintaining the accuracy much better than the previous models. And we also use all of these new data like CFAR 10, 100, the tiny ImageNet and ImageNet 1K, and we compare with these usual suspect, EWC and BIC and ER and GDOM and Rainbow Memory Now. And we also construct our very simple baseline. And compared to all of these methods, our new baseline called CLIP is outperforming all of these methods by a pretty big margin over these data sets. Also, we plot the accuracy over the course of data injection. And as you see, our new baseline methods are outperforming the other computing state-of-the-art methods. And especially these methods are suffering from the accuracy drops at the either task boundaries or accuracy shoot up at the task boundaries, but our methods are relatively having small accuracy drops when the task is transiting. So that is the observation that we have. We also test our methods in the various A, N, and M setup. So here the N is the portion of the incremental classes, and M is a blurry portion. So if N0 and M0, then basically this is disjoint, right? The N equals 100, then we are using everything as disjoint and there's no blurry portion, right? And N equals to 0, then it's purely blurry portion, right? And here, if we set the N equals to 0, 50, 100, then here the M is 10. And when we say M is 10, 30, 50, we set the N equals to 50, which is eye blurry, right? So then in every different setup, then our methods are having pretty good gain over the state-of-the-art, except this case, but here the gain is really marginal to the best performing methods. So we can claim that our methods are overall working pretty well. We also have some components of this baseline of like sample important memory management, memory only training, and adaptive learning rate scheduling and things like that. And these small tricks are added up to make this pretty good number in the continual learning accuracy. To summarize, this blurry setup never introduces new classes. So we propose a new blurry setup called iBlurry with the newly entered class. And we propose a very simple baseline to address either iBlurry, blurry, and disjoint everything, but nothing is very new. So it's kind of the same message as a GDOM is telling us, so that which is by using very simple methods, we are having pretty good performance on the continual learning setups. And continually learned models are only evaluated at the end of the task in the previous literature. So we propose a new metric called AUC to measure the performance at all time to get the better measure or performance evaluation measure for the continual learners. And here we also publicly release our code in this code in the GitHub repo. So you can download the code here. All right, so any questions here? And Vincent, nope, no questions. Or I have another chapter actually.
There's
so
a question.
I'll just stop it here and just get some questions. All right, so Ishing has a lot of questions. Should I read it or?
Oh, I can read it. Thank you very much for this nice talk. Great idea to apply few shot learning and to propose the rainbow memory technique for blurry continual learning. Can you comment on the selection of learning rates? Larger learning rates tend to forget more, while smaller learning rates tend to learn new knowledge slowly. Many methods, as summarized by Lange et al., use a grid search for the learning rate, but grid search is very computationally expensive. Can you tell details about your learning rate configuration or recommend better ways?
That is a fantastic question. So the learning rate is one very important thing in continual learning. And here we are just using very naive way of adjusting or tuning the learning rate hyperparameter. So if you're studying on much more deeply on the learning rate scheduling, then you may get something more in the continual learning. So one lesson that we have learned is to get this learning rate scheduling adaptively as the epoch goes by. So we have used this technique in the rainbow memory, but we have not said it explicitly, but in this clip, we studied this a little bit further and then having the evaluation study result here. So here we see like 1% gain and 1% gain in T4 family data set. So the learning rate scheduling is not super critical, but it is adding up some value when you're having this continual learning methods designing, right? So one lesson that we learned on this learning rate scheduling is to get this learning rate scheduling gradually decreases as the epoch goes by from some initial learning rate scheme. So initial learning rate value, which is kind of popular scheme. So we just use it and it just works fine. And this is a very good research direction. So if you're thinking about just getting this continual learning methods, you also have to think about this learning rate scheduling as one of the components of your methods. But it's not should be the main story of it because the learning rate is not affecting the accuracy that much.
I see. One question that came up when you showed the computation of the uncertainty, I was wondering, right now you do it with known class, right? But
Right.
Can you use that also in an active learning or interactive labeling setup where you don't know the class? Would that also be possible?
Right, that's an open set kind of question, and this is also a fantastic question. And we haven't thought about to use this technique in the active learning context or some kind of open set kind of context, but you can think about it as an open set kind of problem as well, because you're seeing a new class as the task goes by. So if you're applying this method to the open set problems or the active learning problems, that it may be helpful as well, but we haven't tested yet.
Interesting. Wow.
Yeah.
There's one more question here in the chat. Thank you for this very interesting presentation. I find the AUC metric really interesting. Would it be possible, in your opinion, to use it to keep an optimal balance between the new and old data in the training?
Right. Here, the notion of optimal balance is an open question, right? So if you know the optimal balance, then, or if we can find it, then it would be great. But I don't know how to get this optimal balance between the new and old data in the training. So it's not an easy problem.
So
Vincent also asked another question. Is the bipolarity task really so new? Isn't this well known in an open world setting? I think it is well known in open world setting. I agree. But it's not tested in the continual learning context yet. So we have proposed it as a new name as bipolarity. But it's the same thing.
I would also be interested, you've shown that uncertainty is better than prototypes. Do you think this is related because you're actually in uncertainty also measuring the effect of the augmentation, which is neglected if you compute just prototypes?
The prototype could be another thing, but in practice, we also compare with this prototype-based sampling method, but in the table, as you see, the uncertainty-based method is having much better performance in practice.
Yeah, and I think it's because the prototype is not able to quantify the effect of the augmentation during the training process. And this is where uncertainty is much better because it knows about the augmentation, right?
That is true. That is true. But at the expense of computation of all the confidence on the transformed data. And surprisingly, when you do this balanced random sampling, your performance is similar to the uncertainty-based method, like 1% worse or 2% worse. So here, this random sampling is not balanced between the classes, but if you sample it randomly balanced in a balanced manner, then your performance is very similar to the uncertainty based method, which was kind of surprising. Later we found. So in that case, it is not also explained why this uncertainty is working better than the others. It is still the open question. We're still digging into it, but we don't get the answer yet. So hopefully we can get some answer and also report it to the community later.
Interesting. So you had in the continuous evaluation, in some methods, you had this huge jump towards the end of the task. And I was wondering why you see such a jump in performance towards the end of the task.
That is a great question. And we found that this is only the big problem in the rainbow memory, which is our methods. The rainbow memory is a two-stage method which stores the data in the episodic memory and just keep it and not use for the model updates until the end of the task. And when the end of the task is coming in, then we use all the sample in the episodic memory and we update the model. So that's why the accuracy shoot up at the boundaries, only for the rainbow memories. But the other methods like the GDOM or BIC and EWC, they are experiencing the dropping the accuracy at the boundaries. So they are updating the model. They can update the model on the way that the data is coming in the episodic memory, but they are also experiencing this drops at the task boundaries. But our method does not suffering that much of the drop, even though we also have a drop, but the drop is smaller than the previous method, so that our method is maintaining the data much more continuous manner, so that the drop is not much significant. That leads to the higher accuracy at the end of the day.
Now, given your huge experience in continual learning, and what is your opinion on the lottery ticket hypothesis? That, I mean, learning processes are kind of taking this random initialization, and then the learning essentially reinforces the good weights that have been randomly initialized and just forgets about the other weights. What do you think about it?
I think the continual learning is also contains or also subset of the problem of the learning the things, right? So this is inevitable in the continual learning as well. So this is another kind of lottery ticket, I guess. Yeah, but it's more realistic setup than just one-shot training. So maybe getting the lottery ticket is much more challenging than just one-shot learning. That's why we may have some other method to getting better lottery tickets in this continual learning setup. So that's why we just propose, A and B, things like that. Yeah, I have one more part, so let me finish this and just
absolutely. Thank you.
Yeah. So the third setup that we are thinking is that this continual learning setup, which assuming that the data is coming in the online stream, is assuming all of the data annotation is correct. But this data stream is going to be assuming that like on-the-fly annotation by the human annotator when the data is coming in, right? So in that on-the-fly kind of scenario, that the human labeler will make some errors in the label. So we now try to study that the situation if the streamed data has wrong label. So we name it as noisy label continual learning, which was presented in this year, CBPR. So here we try to use the same idea to diversify the visual information in the episodic memory. But if you're enforcing this diversity in the episodic memory management, we're gonna be having high emphasis on the wrong label data, right? So it's a kind of analogy of this kind of fairy tale. Do you have this fairy tale in Germany as well? You have this bunch of
the ugly duckling, right?
Right, ugly duckling, exactly. This is ugly duckling story. So with a bunch of ducks, and we have a swan here, right? So this swan is basically labeled as a duck, right? And this swan was like suffering. Yeah, why I'm not an ordinary duck, which is actually a good thing, but he was like he or she was very suffering from it. And when you enforce the diversity, then these wrongly labeled samples will be selected to be incorporated in the episodic memory, right? So if you are diversifying the visual information on the episodic memory, on the noisy label scenarios, then you're only selecting these kinds of bad samples or the samples with the long label, usually. So by just using the diversity without any consideration will give you much worse performance than just purely random sampling or the other sophisticated methods. So we just think that, yeah, let's try to diversify sampling, but with a little bit of consideration of the label noise. So we get this stream data and we partition them into three different subsets, C, R, and U. So we get this C, so we compose this C set as a confidence set. So if you have the sample in the online stream and then put it as an inference to the currently trained model and get the confidence. So when the confidence is enoughly high, so let's say we have this having some threshold of the confidence set. Let's say the confidence of your sample is going to be more than 80%. Then we put it as a confident sample, right? And the R set is the sample that has a confidence in between like 40% and this 80%. So these sets are having a chance of wrongly labeled because it is not giving us the right confidence on that designated classes with the high confidence. Maybe it is not fully trained yet, right? We don't know, but maybe it is coming from the wrong label. So with the help of robust learning literature that cleans up this label, right? So there are a lot of techniques to clean up the label. Yeah, maybe this data is going to be newly labeled or clean up the label to the other one. And we use the same technique to clean up the label of these samples and relabel it to be used as a supervised training. We call it as a relabel set. And we have the other samples that has the confidence of lower than the threshold of very low, like 20% or something. Then we assume that, yeah, these samples are highly likely super wrongly labeled, right? In that case, we are taking out the label and use it for the representation learning, which we name it as an unlabeled sample. So here we partition the streamed data into three different subsets and then use our diversifying the sample memory management scheme for the C set and R set with the cleaned label on the R set. And U set, we don't use any label and just use for the representation learning and get the value, get the accuracy. So for the little bit better, fair comparison to the previous art, we combined with the robust learning technique to clean up the label with the previous prior art of the continual learning methods. So we combine RSV, the continual learners, with the label cleanup method of selfie and co-teaching and divide mix. So at the end of the day, the label cleanup method that we are using in our methods for the R set is co-teaching. So here, the divide mix. So we end up with using the divide mix for the relabeling. And on different level of noisy portion of the data, the CFAR10, the symmetric noise of 20%, 40%, 60%, asymmetric noise of 20 or 40% on CFAR100 as well. Our methods are performing all of the prior arts combined with the label cleanup methods by pretty good margins here, especially with the high label the noise situation. Right, so that's the end of the story. So the sample diversity noisy label needs to be reconsidered. So we propose to divide or partition the data stream by the three subsets and treat them in different manner to implement a diverse sample in the presence of the label noise in the episodic memory management. So we also publicly release our code in this GitHub repo, so you can download it pretty much to reproduce the numbers. So here is the takeaway of these three parts of our attempt to make the continual learning much more practical. So the first one is episodic memory management policy needs to be reviewed. So the rainbow memory and the Puri diver, the last method we name it as a Puri diver, is a purifying diversity episodic memory replay method, or something else. It's like very complicated name. So we propose this episodic memory management scheme, which is pretty simple. And also we question the popular setup in continual learning, which is a blurry setup, to propose a new setup called the iBlurry. So here I want to say to you that we have to think that whether the literature is moving in the correct direction to solve actual practical problem or not. So instead of just trying to get better number on the well-designed method, which may be not well-designed task, which may be not well-designed for the practical purposes, maybe working in the lab environment only. So we have to reconsider or rethink whether we are doing something meaningful for practice or not. So scenarios that we take granted may be not realistic. So you have to take it back and think about the problem of interest that you're trying to solve is actually meaningful or not to make the advancement in computer vision or machine learning. Right?
Well, thank you very much for the presentation. It was very, very didactic, and I think many of our colleagues have not been working so much in continual learning, but I think many of the sampling methods and also, measuring the uncertainty and the confidence in a sample is something that is very, very applicable to everywhere in image classification or general machine learning, right?
Thank you. Yeah.
Particularly the Puri driver, we have, in particular in medical, we have so much problems with noisy labels.
That is true.
I think this is something we will definitely look into, seeing whether this method can help us in identifying, poor samples, in particular in the age of like big data, and that some companies are working even in medical now with 100 million images in the training data, and it's really massive amounts of performance increase that we see just by the immense amounts of data that are now available under unfortunately only to the companies, not so much to the general research public.
Right. But outside of this continual learning context, you can still use this idea for cleaning up the data or tackling up the few shot scenarios.
Yeah, absolutely. And I think like everybody of us has these problems and is dealing with that. And also the idea of measuring the diversity in the set is also, it's very appealing. I have to think about it a little, but I think I can see at least 2 or 3 different applications where it would make sense to go into this direction. So
thank you very much. Yeah, I'm glad that you like this idea of making the diversifying the samples in like few-shot learning or semi-supervised learning or pseudo-labeling and things like that.
Did you also think about investigating this in like image generation and things like that?
Oh, I was thinking about it using this for the generation, but in like my personal preference is not going to the generation direction, because for getting like very visually appealing generation methods, we have to get a lot of GPUs, and in school it's not available for me. So I pretend not go to the generation direction, but if I have enough resources of GPU, then why not? I would love to use it for generation.
So in medical, we often have the problem with anonymization of data, and generation is potentially a way out, right? So
that is great. Yeah, that's right.
Official samples that can then be shared. But of course, you want to make sure that they are not too close on the original data, right? Because some of the generation methods are bound to create samples that are very similar to what they've seen in the training data. And I think the diversity measures can also very nicely be used in
alleviate that problem.
Such a context. I mean, it's not the same, so we have to think about how to adopt it. But I think what you've shown is very stimulating. Very, very cool research. I like this a lot.
Maintaining the same semantic meaning but visually different output or sample generation will be very interesting, important directions in the context of this medical privacy data, I guess.
Exactly, and we can measure the anonymity by re-identification approaches automatically.
Oh,
And then
right.
on the other hand, we need to have good utility that the task is solved well.
That's
And
right.
and this is very interesting approach.
Yeah. So I'm always looking at these kinds of problem. So if you were having some good, nice work to collaborate with, then yeah, I'd love to discuss with Professor Meyer for that.
Absolutely.
And we have also other things coming up, and we just put it up everything in our website. So you can please visit our group's page by clicking it, and also always email me about some questions and comments. And I also have some personal page to have all the papers lined up. Yeah, thank you. And this is all of my colleagues, and my groups are growing. Thank you for your attention today.
Absolutely. And I have a round of applause for you. I hope this works. And you
Yep, I can hear that. Thank you very much.
So in Germany, we have the tradition of knocking the table as applause.
Oh, I see.
Now you have a virtual knock because otherwise Zoom typically cancels it.
That's right. Hendrik is giving me this icon. Thank you.
Yeah. Thank you very much for the presentation.
Sure. Thank you very much to invite me.
Jonghyun, thank you very much for this brilliant presentation. I must admit, I learned a lot during your talk, and I think it's really exciting how to process data in a way that you continuously learn and which samples to keep and how to design architectures in order to make them not have to suffer from catastrophic forgetting. So Jonghyun, thank you very much for this. I think this was a brilliant presentation, and I'm very much looking forward to welcoming every one of you back to a next episode of Beyond the Patterns. Thank you very much for watching, and goodbye.